I'll record this. Regarding the tests, we are going to have, 19 this week?
Yes.
And then
20 next week.
20 next week, and then final exam the week after that?
No, chapter 25.
Is it 2 weeks after that?
Final start on May 13th. So
We have 3 weeks left, right?
yeah.
And so we have this week, next week, and the week after that, correct? All right. Then this is the way the tests are going to work out for the remaining semester. We're just going to have a 19 this week and a 20 next week. 20 is electrochem. And then 24 and 25 will go on the final.
So does that mean the final's going to be worth more? Or?
No.
Okay.
Well, maybe I should make it worth more, huh?
No.
What are you doing? What are you doing, dude?
You could make up points that way. 24, we're just doing half the chapter, and then 25 is going to be a survey of nuclear chem. Is what it is.
You're still going to finish lecturing on those chapters, right?
Yeah.
Okay.
Yeah, I'm going to finish lecturing on those chapters in the next 3 weeks. And chapter 20, we're going to finish chapter 20 this week. Tomorrow I had this molecular probes lab scheduled, right? But with what happened with Spartan, we weren't able to get as far as I thought, and so we're going to have to drop that. I'm going to drop that lab.
Okay.
Although I hate dropping that lab because I think it's an interesting lab.
So are we turning in anything related to what we did with that one, or are you dropping it completely?
Dropping it completely. I'm not even going to send out the handout.
For OCHEM, I heard that Amy Grant is retiring.
Oh, yes, that's true.
Is that true?
Not retiring.
Okay, she's
Getting promoted.
not. Or she's okay. So
She's
not
being
teaching,
interim
right?
dean, right? She's not teaching. Was she scheduled to teach 7A?
Yeah, she was.
Yeah.
Next.
What's up?
The 7A instructors to be announced. Yeah. So it'll be somebody. I'm not sure who's going to teach the 7A.
Do you do 7A at all?
No. I won't be teaching it.
Who are the
Maybe.
professors out there?
It depends. Actually, there are going to be 2 new professors here starting in the fall. Yeah. So we'll see what happens. I'll just go ahead and register for a class. Speaking of organic chemistry, there's a seminar. I wasn't sure if I was going to announce this or not because of other reasons. One reason is this seminar is organic chemistry. Another reason is because somebody's going to ask for partial credit. I'm sure. Or they already did, or extra credit. That's right, not partial. Extra credit.
Just turn it down for you. It's a seminar for No, that's what he's saying. He said he was hesitant on getting it out because people asked the question.
I think the R said should we do
No, that's true. That's a little different.
Hey,
People already did ask for extra credit in this morning.
But we're the cool class. We're not going to have extra credit.
Oh, really?
Yeah.
Wow, that's very cool.
What are you doing?
Good. This.
Come on. Gotta get some energy.
I'm not sure how worthwhile. I mean, this is really interesting stuff. But for helping you for Chem 1B, one thing might help would be chiral, dealing with chiral compounds. Have you heard of chiral? Chiral is a type of isomer Let me see. That has a handedness to it, like a left hand and right hand type isomer. And so in that sense, it might be worth it. Or if you're interested in design, drug design, then definitely it's worth it. Okay. All right, so if you're interested, check that out. No, just check it out if you're interested in. All right, any questions?
Concerning the visual medtech lab, what do you want us to turn in? Because I don't think this class did too well on that lab.
Yeah, could we replace that with the Spartan lab?
No, both labs. You have to do both labs, visual MinTech. I know, actually, in the morning class, I know some people are still working on their visual MinTech calculations. So I haven't announced a due date yet for that, because they're having some problems with the application. But are you guys all finished with visual MinTech? No?
I feel like this whole class, I don't even feel got past the first step, right?
With visual MinTech?
I don't think we even wrong.
Oh, really? All right, then I'll open up the computer lab tomorrow after a lecture. I'm going to do some catch-up still in the lab. I won't use the whole period, so you can go in the computer lab and finish your visual MinTech calculation.
Is this still separate from our lab reports, like from our next lab report and stuff like that?
Yeah.
Okay.
I had a question this morning about the lab. You know, the Le Chatelier's one, just leave that in your notebook. I'm going to be checking notebooks for observations. So, you know, when I look at the Le Chatelier's, I just see, you know, what kind of observations did you get when you added acid or when you added this, added that. And so that's how I'm going to grade that one. So you don't have to turn in a report for this. One person did turn in a report, filled it out. But if you have the report already filled out, go ahead and turn it in. I'll look at that instead. All right, that's the Le Chatelier's, and then we have the visual MinTech. Visual MinTech, some people were asking, what do I want to see? And you did two things. One, I want to see your homework calculation. Two, I want to see the visual MinTech calculation. The visual MinTech and the homework should give you the same answer, did they? It would be nice if they did, you know. If they did, then you say yes. You got the same answer. Everything worked out nicely. If they didn't, I want you to say a few words about it. You know, and so, in other words, I want you to compare your answer with Visual MinTech's answer because they're both supposed to come out the same, or were they? Were they supposed to come out the same? The Visual MinTech and your calculation, were they supposed to come out the same? Yes and no. Yeah, yes, because it's a. Actually, you're supposed to be answering this. You're supposed to be figuring this out, right? And so this is what you have to figure out. And so you need to comment. You know, this is like a compare and contrast kind of deal. Compare and contrast the two answers and comment on them. I'll give you some hints, you know. Some hints. Let me give you one hint, and that's it. Ideal gas law and real gas law. Do they come out the same? Why? That's it. That's my hint. All right. I don't know how much I've been harping on that same point over and over again, so I don't want to do too much, but it's along those lines. Okay.
What's the bit about Le Chatelier's notebook? That's still in our lab notebook, right? when you say that, when you're talking about Le Chateliers, is that going to be, that's still in our notebook from our lab, that's still like turning in, or do more for it?
No, you don't have to do more. That's
Okay.
it.
Okay.
This, you know, there are different aspects of lab. You know, not everything's going to be graded on the report, because not only do you have to be able to write a report, like a formal report, or just a brief report summary, just kind of here. But not only do you have to be able to do that, but you also have to be able to take observations too. And so this particular lab here, the bulk of it is going to be based on your observation in your lab notebook. In fact, I'm going to be collecting your lab notebook the last week of class. I'm going to give it back to you, but I'm just going to look and check your observations, not just for the Le Chateliers, although all your points are going to be wrapped up in there, but the observations for the other experiments as well should be in your lab notebook. That's all. And so Le Chateliers, assuming you took observations, you don't have to do anything extra. That's it. You know, Le Chateliers, it just shifts this way or shifts that way, or the color changes this way or that way. That's it. It's a pretty simple experiment. Visual Mintac, you know, a lot of people, they just turn in this, you know. They do their calculations, they show the Visual Mintac and turn it in as is, with no commentary. Some people will comment on this. Some people are really gung-ho. I don't expect it. And one semester, somebody turned in like this 5-page deal on this, you know, talking about this. But I don't expect anybody to do that. But it was nice. You know, they did a really nice job on that particular lab. Talking about the calculations. You know, if this were a formal report, what would you write? Fortunately, it's not a formal report, so you don't have to write much. Just a brief comment is good. So, everybody's not done with this. So, okay, so we need more time. And so you should be able to finish the calculation part of Visual Mintac. You can also do this one at home easily, because Visual Mintac is free. You know, you download it onto your computer, do the calculations at home. It doesn't take up much space either for the database. Okay, then we have the Spartan acids lab. What do I want you to do with that lab? Nothing?
No, you said you were.
You were dropping Spartans.
No, I'm dropping the Spartan molecular probes lab. We have 2 Spartans lab. This one is the Spartan acids is the introduction to Spartan. Spartan molecular probes is the application. We're going to use what we learned from the Spartan's acid to be able to do.
So the Spartan acid is the one where we found the R squared that's still going to be needed.
Yeah, sorry. We had 2 Spartan labs. The one I had scheduled for tomorrow is the molecular probes lab. That one we're going to drop.
Okay.
Well, you should be thankful, because the Spartan molecular probes lab is much more involved than the Spartan's acid
We
lab.
did when we originally did Spartan, because we're not doing the one tomorrow. You're dropping.
Yeah, I'm dropping tomorrow's Spartan lab.
For this Spartan one, I thought you wanted us to attach it to our lab notebooks and then put the Lewis structures in the lab. But you said,
Inside the lab notebook?
did you want to cover it?
Well, then make a copy of it and then give it to me. That would be it. But what you have to do for the Spartans acids lab is we have to look at acid strength. And so, what the purpose of the Spartan's acid lab is to collect a whole bunch of numbers. You get a whole bunch of numbers and then you see, are any of those numbers correlated with acid strength? And so what kind of numbers can you generate? Well, we can generate lots of numbers with Spartan. We could also generate some numbers by drawing the Lewis structure. And so if we compare two acids here, although the first one is familiar, acetic acid. The second one I'll draw, maybe not so familiar as an acid. Well, what kind of numbers can we generate when we look at this? This is what I want you to do. I want you to write the numbers that you can generate by hand without using Spartan. And so what kind of numbers can you generate by hand? Formal charge?
Oxidation state.
Oxidation state. So the formal charges are all 0. Formal charges we circle. All the formal charges is 0. Does that tell us much? No. And then we could generate the oxidation states. What are the oxidation states? Hydrogen?
1, 0.
+1. Oxygen?
+6.
-2. This oxygen? -2. This carbon?
Is it 1 plus 1
No.
plus
Oh, sorry, no, it's +3.
+3. +3. Actually, this is all I asked. In the past, I've asked for all of them. But let's go ahead and do all of them since I'm doing. +1,
plus 1
+1, +1. Actually, no, I didn't. I asked for 2 atoms, remember? This carbon and this carbon. Did you guys record that in your notebook? You should have. Because this carbon, is this +3 also?
No.
No, what is this carbon?
0. 0. 0.
Not 0.
7 plus or minus 3.
-3. This carbon's -3. It's quite a bit different, these two carbons. You see that? Well, what do these numbers tell us? They tell us something about how the electron density is distributed in the molecule. Formal charges assume what kind of bonding? Formal charges assume covalent bonds, right? Covalent bond, that means this, when we look at the formal charges, the electron density is spread out evenly in the molecule. Oxidation state assumes what? Ionic. So when we look at the ionic bonding, if we assume the bonds are all ionic, this is the electron density distribution we see. But the reality is that this is not 100% covalent, nor is it 100% ionic. It's got some kind of percent ionic. Do you guys remember the correlation in Chem 1A between delta En and the percent ionic character? We got chapter 10. There's a correlation between delta En, the difference in electronegativity, and the percent ionic character. And based on that, they come up with some rules, like if it's less than this, it's non-polar covalent. If it's between this and this, it's polar covalent. It's based on this chart. Oops. And it looks like this. This percent ionic character versus delta E. The correlation is not great, you know, it's okay. It's just a rough correlation. And if we were to track it, it looks like this, but there are a whole bunch of points. And the R squared would be pretty bad. But still, there definitely is a rough correlation between these two. Well, it's neither 100% covalent nor 100% ionic. It's somewhere in between, and that somewhere in between we use this. Rather than a full -2 or 0, you know, the charge is going to be somewhere between 0, its formal charge, and -2, its oxidation state. And that charge is what we call delta, it's partial charge, delta minus, somewhere between these. Charge on hydrogen is going to be between 0 and +1, so we call it partial, delta plus. And so we can get these kind of things from this. So just some idea, but we don't have an actual number. With Spartan, we can get an actual number for these. All right, and then let's compare that to this molecule here. Let's just compare the hydrogens, the two hydrogens here. They look similar. This has a 0 formal charge. This has a +1 oxidation state. So this one will be delta plus. This oxygen looks very similar. 0 and -2. And so do you see this part of the molecule looks the same? And so there's going to be a delta plus here in the hydrogen and a delta minus here in the oxygen. So there's just going to be somewhere between there. But this is acetic acid. This is ethanol. Is ethanol a very good acid? No. In fact, ethanol has a Ka that's so small, you know, we don't really consider it acidic. It wouldn't be very good at neutralizing base. Although it still can be attacked. A very powerful base can come along here and pluck that hydrogen off. It would have to be an exceptionally powerful base. And so it looks very similar. Oh, there's a carbon here, right? There's a carbon here. And so structurally these look very similar, except there's got to be a difference. And so here we could see a difference immediately. This carbon has a formal charge of 0, but an oxidation state of, the oxidation state of this carbon. -1. So do you see a difference there? And this isn't easy because we got a lot of numbers here. And so this is why I was trimming down the numbers somewhat. I didn't ask you to get all the numbers. In the past, I've asked for all the numbers. So that's why I end up getting a lot of analysis. But it's like this. At first, you got a bunch of numbers, and this bunch of numbers doesn't seem to make sense. It just seems to be a lot of confusion, and everything seems to be mixed up. And so what this is similar to is one type of scientific method. On past tests I've asked, what is the scientific method? And a lot of students will say the scientific method consists of making a hypothesis and then testing the hypothesis, right? Making the hypothesis and then testing the hypothesis. And so you already have the question in mind, and you already have what the answer should be in mind, right? You're going to be testing it. But a lot of things we don't have the question or the answer in mind. What we want to do is we want to see, if there is any kind of connection between these numbers and the acidity or whatever else. And so this brings up, like, for example, electron energies. Do you think in the development of that theory, quantized energies of electrons, do you think they first proposed the hypothesis? Somebody came up with a hypothesis that electron energies are quantized. No, I mean, who would ever think of that? Nobody. And so oftentimes what you do in science is you just look at a whole bunch of data and then try to reduce the data. Have you ever heard of data reduction? Well, as you continue on in science, you will hear about data reduction. You might even read a book. There are lots of books about data reduction. And what data reduction is you just take all these, I mean, this is just a jumble of numbers, right? You take all these and reduce it. Well, what do you reduce it to? Well, this would be like soup. You're reducing a soup to its essence or whatever. Like a bouillon cube or something like that. That's all soup is. It's this flavor. Well, the same thing here. You got a bunch of these numbers, and what you need to do is you need to reduce this down. This is data reduction. This is part of being a scientist. Is you got to be able to do this. You reduce it down. Well, you have a hint, about how to reduce it. Well, one way of reducing it is to try to correlate the polarity, the hydrogen to its pKa. But some things aren't going to help us. I'll tell you. For example, formal charge. Does formal charge give us any information about why one acid is stronger than the other? No. And so one way to reduce this data down is not even bother. The formal charge doesn't tell us any additional information, etc. And so what you're going to do in this lab is, you're going to make a plot of the pKa versus the polarity of the hydrogen. But you also want to look at some of the other things, because when you make that plot, did the plot come out perfect? Was there a perfect correlation between pKa and polarity? Unfortunately not. Unfortunately there's some outlier. Something that it was looking good. I mean, if you could get rid of this point, your R squared would be actually pretty decent. What's the R squared you guys got? 0.98. 0.98. You'd probably be in the 0.99s if we just reduce this data set. Just get rid of that. And then the correlation looks great. But you're not allowed to, unfortunately. You can't just eliminate that data. This is not part of data reduction. Data reduction is something else. It's just coming up with these patterns, that's all, rather than jumbled numbers. What is a pattern? Hopefully, here's one of the patterns. But if we have this outlier here, there's got to be a pattern to that too. Why is this one not like the others?
Exception is special.
Well, if it's an exception or special, can we find that in the numbers here? That's what we're looking for. Is there something in the structure that tells us why this one is behaving differently than the others? So this is why I asked to collect a bunch of numbers. So you collect a bunch of numbers, so hopefully you might be able to see. Maybe you won't be able to see anything, that shows why we have an outlier here. Did you guys see an outlier? Yeah, one data point that kind of throws off the R squared? Yeah. And so what we'll do is we'll look through the numbers, and then, maybe the numbers aren't going to tell us anything. And then we might have to dig deeper into this. If we dig deeper into this, then we have to go back and look at what makes a strong acid a strong acid. And so we go back and review. This is supposed, I didn't cover this in Chem 1B. It's supposed to be covered in Chem 1A, acid strength. What's the most important factor influencing acid strength structurally? Yeah, we want to deprotonate the acid. And so deprotonating an acid, the number one thing, I'll just review it a little bit right now, is the bond strength. Now, how easy is it to break that bond? And so the example that should have been covered in Chem 1A would be something like this: HCl, HI, HBr, HF. You're supposed to rank these acids. Rank these acids from strongest to weakest. Which one would be the strongest of these? The strongest of these would be HI. HI is the strongest, followed by HBr, followed by HCl, followed by HF. HF is an outlier. HF is way weaker than the others. And so this pattern's easy. You know what this pattern is? This pattern is HI has the biggest atom here, weakest bond. And so to break the HI bond doesn't cost much energy. HBr has a little stronger bond, therefore it's going to be less acidic, it's harder to deprotonate. HCl, well, actually all these are fairly easy, but HBr would be slightly harder, HCl slightly harder. So it'd be a slightly weaker acid. HF is a way weaker acid. Is HF a way weaker acid because its bond, it's got like 1,000,000 times, HF is 1,000,000 times weaker than HCl. Does that mean HF's bond is 1,000,000 times stronger? That is, let's say HCl's bond is like 300 kilojoules, and this would be 300 million kilojoules per mole to break. Does that make sense to you? No, and so now we got all this data, right? And now we got to figure out what the pattern is. And so we start to look, why, especially why is this one not behaving like the others? Does anybody remember the reason why HF doesn't behave like the others? Well, when we think about electronegativity relates to ability to attract electrons. And so what attracts electrons here? Well, the hydrogen's going to attract electrons. So all these are hydrogens, so they should all have the same electronegativity, the hydrogen. I'll talk more about electronegativity because electronegativity is used to talk about other things too. But the reason why HF is an outlier is because of ion hyphen or ion. It's because of ion pairing. The hydrogen has a hard time breaking off. Even though the bond is not 1,000,000 times stronger, it's just when you break it, it just doesn't completely break because the hydrogen sticks around. So it's ion pairing that causes this one to deviate from the trend. Not only do you have to break the bond, then you have to break this ion pairing attraction, which costs additional energy. And also, this inhibits this from reacting with other species. So this is a secondary step. All right, so we look at bond strength first, and then we look at bond polarity. Bond polarity. this is a case where the bond strength should be the same. So let's compare these two acids. Hypochlorous acid with hypoiodous acid. Which one's stronger? Well, it's got to be hypoiodous, doesn't it? Because this was hydroiodic acid is stronger over here. Is that correct? No. Which one's stronger? Hypochlorous acid is stronger. Why? Well, because the OH bond should be about the same strength in both of them. The difference is the polarity of hydrogen. This is a polar bond, you know, delta N. But this one's going to have a bigger dipole or positive charge than this one. Why is that?
The electronegativity of the chlorine.
Yes. Electronegativity, here is electronegativity work. Electronegativity of chlorine versus iodine. Iodine is a lot less electronegative. And so iodine isn't really going to suck the electron density like chlorine does. If chlorine sucks away the electron density from oxygen, what's oxygen going to do? Suck it from hydrogen. So that's going to make it, we call this effect what? We call this the inductive effect. Chlorine's more electronegative, holds more electron density, in turn makes this pull. Iodine is less, doesn't pull as much electron density. In fact, iodine versus oxygen, oxygen is more electronegative. So I'd actually have to flip it. Actually, chlorine too. Well, we'll just leave it like this. It's a good terminal. It's a less inductive effect. Does that sound familiar?
Yeah.
Okay, good. And so a base is going to be attracted to hydrogen. It's going to be attracted to this one more than this one. All right, is that the only thing we look at? No, there's more. But what else do we consider? Consider the stability of the product. The stability, in this case, the product is the conjugate base. Stability of the conjugate base. The more stable the conjugate base, the stronger the acid. And so looking at the stability of the conjugate base, maybe the first thing we can look at would be the, let me just give you an example here. Sulfide versus oxide. Which one is a stronger base? I guess you could look at the chart, but probably you wouldn't have to. Oxide, why? Which is stronger? Why is oxide stronger than sulfide? Yes. Did you guys hear that? Bigger hunger for positive charge. Yes. that's exactly right, except I wouldn't have said it that way. I would have said it a different way. Yeah, this one is going to be a better hunter of protons. No, I wouldn't have said it that way either. I would have said, what? I would have said this. That's an oxide that has a higher negative charge density. So the first thing we look at in the stability of the conjugate base is charge density. The more negative charge density, the more it's going to want positive charge, right? Why does the oxide have a higher negative charge density?
Small.
It's smaller. It's got the same size charge, but it's smaller. And so the more concentrated the negative charge, the less stable the base is. And so this is weaker and more stable. So when we're looking for stability, we want, we don't want high negative charge density. We want low negative charge density. And the lower the negative charge density, the better. Sometimes the negative charge density looks the same. And so we look at this. So for example, if I look at hypochlorite, which is a base, versus hypoiodide, both on oxygen, right? But they aren't the same strength. Which one is stronger? Which one's weaker? The stronger one, less stable, higher negative charge density. The weaker one, more stable, lower negative charge density. Yeah, this one's going to be more stable. Or, you got to rethink that, because having the negative charge on the oxygen is going to dictate it. Both of these appear to have -1, but they don't. They don't because of what's bonded to it. And what's bonded to it can suck electron density away. And so what would suck more electron density away? Chlorine or iodine? Chlorine. In fact, iodine's not very electronegative. We have something like this. This is exaggerated, obviously, but if there's a tug of war, what's going to happen is oxygen is going to come out less than it would over here. Well, if chlorine's sucking more charge density away, then it's going to lower the negative charge density on oxygen. And so this one's going to be weaker and more stable. This one's going to be stronger and less stable, because here the negative charge isn't really pulled towards the other atom. This is called the inductive effect. Look at an inductive effect. But what's more significant is something called resonance delocalization. what happens is the inductive effect is going to reduce the negative charge a little bit on this one, whereas it's not really going to reduce it much on this one. Let's take a look at two of these bases that we'll see from the previous example, and that is acetate is what we get when acetic acid loses a hydrogen. It's going to be negative here. Versus this one. When ethanol loses a hydrogen, let's say a very powerful base comes along and plucks that hydrogen off the oxygen, and we get this. Both of these have a negative charge on the oxygen. One of the things we could state is the inductive effect. You know, what was the not the formal charge? What was the oxidation state on this carbon? -1. -1 carbon. What's the oxidation state on this carbon?
It was negative. It was +3.
+3. So this is a -1 carbon. This is a +3 carbon. So we have the inductive effect. What is an inductive effect? Inductive effect is electron cloud withdrawing effect here. And so over here we call this electron withdrawing carbon because it's going to suck electron density away from the oxygen, making it less negative. Over here, does this -1 carbon suck much electron density away? No, this is what we call electron pusher. It's not really pulling electron density, it's pushing electron density onto the oxygen, making it even more negative. And so, based on the inductive effect, you'd say the right one is a stronger acid, correct? But there's something more dramatic about this one, and that is resonance delocalization. Acetate has another resonance form we can draw out for this. The other resonance form is going to look like this. Now this oxygen has a negative charge. And so what we can do is we spread out the negative charge. It's on this oxygen or this oxygen. But we know that neither of these is the correct. What would be a more accurate drawing, a depiction of the structure? The mix of both. And so that would be the hybrid structure. And so what would the hybrid look like? The hybrid structure is going to look like this. Where the double bond is evenly spread out over both positions. You get something like this. And the negative charge is spread out over both oxygens. And so we go from a -1 formal charge to a -1/2 on each of the oxygens. And so what do you think has a more dramatic impact on stability? The inductive effect in this case, or resonance delocalization? Resonance delocalization. Inductive effect is still in play here because this carbon is still positive. But for sure, this is going to be much weaker, much more stable base than this. In fact, this base here is called ethoxide. Ethoxide is as powerful as hydroxide. You know, acetic acid, which forms acetate. Acetate's nowhere near as strong as hydroxide. Those are quite a bit more stable. sometimes we have to use a combination of both these to explain. So let's look at both the inductive and resonant. Looking at the stability. You recognize this?
Is it a what?
Well, this is benzene. Sometimes benzene's written like this. Alternating double bonds. The double, single, double, single. These are all carbon atoms at the corners here. The hydrogens aren't shown. This is benzene. But benzene has two resonance forms. And so the true structure would be more like the hybrid, where we spread out the pi bonding electron over the entire ring. This is a class of organic compounds called aromatic compounds. This is what happens when you have these alternating single, double bonds. All the p orbitals line up. And so you can get delocalization of the pi bonding electrons. Well, let's take a look at this acid. It's not, you wouldn't really think of this as an acid. It looks like a alcohol, doesn't it? And so this should be like ethanol, right? Ethanol, in a lot of respects. So you wouldn't consider it very acidic, but you know, this is an alcohol that is unusually acidic. Unusually acidic. So do you want to generate a hypothesis for me and then test it? Let's test it. So go ahead and generate your hypothesis. You probably aren't going to come up with a, so what we do instead of generating a hypothesis is we just look at all the numbers we can come up with, or look at all the structural features we can come up with and try to make some kind of correlation. That's what we typically do. In fact, otherwise coming up with a hypothesis is very difficult. You know? Unless you already know. If you already know the answer, then yeah, it's easy to come up with a hypothesis. And so, well, we know this is unusually acidic. Why? Why is this unusually acidic? So we try to figure out, you know, is there some kind of pattern there we can correlate? And so this would be kind of an outlier. You know, the pKa or the pKb would be way off, because when I look at this bond, you know, what's special about this bond? Well, this bond just looks like this. We come up with the numbers. The photometer is all 0. The oxidation state is +1, -2. What about this carbon? What's the oxidation state of this carbon? Is it +1? Let's count. 1, 2, 3, 3. You're right, it's +1. And so maybe that's it. Maybe because that carbon is +1, we have a little bit of that, what do we call that? Inductive effect going on. But is that enough to explain? Because it turns out that this alcohol is even more acidic than acetic acid. And so acetic acid is fairly acidic. Well, this is an alcohol that. And so is that enough to explain that? Well, let's see what else we can come up with. You know, that could be one of the reasons because it's more polar. And so we throw this on the polarity curve and see, does it fall in line on the polarity curve or is it off, is an outlier? Because not only will polarity impact the acidity of an acid, but what else impacts the acidity of an acid? Bond strength. Well, we're just looking at an oxygen-hydrogen bond. What else? Stability of the... And so maybe we should start examining the conjugate base. See if we can see something in the conjugate base that might tell us why this is an unusually, or not why, but you know, how this can be an unusually strong acid. So, what does the conjugate base look like? Well, I'm just going to do this organic shortening instead. So I'll just pick one of the resonance forms. Just like this. How does that look? Can I draw a resonance form like acetate? No. I do have some inductive effect going on, right? But this looks to be as acidic as ethoxide, something like that. Maybe less acidic because of the inductive effect, but do we have much? Well, some of that electron density is going to be sucked into the ring, the carbon here. And that could help. So for example, if I had an acid like this, put a chlorine here. Would having a chlorine here make this more acidic or less acidic? Or maybe make no difference at all? The chlorine's kind of far away. What do you think? I would say it would make it maybe more acidic because chlorine is a electronegative species. If it sucks electron density, eventually it'll pull on the oxygen, which pulls on the hydrogen, making this more polar, making it more acidic. How about if I threw a chlorine over here, the opposite end? How will that impact the acidity? Well, maybe more of the same, you know, the inductive effect, right? But this is different. It's different because of this. Do you guys remember the hybridization? Like, for example, what's the hybridization on the oxygen there? sp3. sp3 oxygen. On these carbons, what are the hybridizations on the carbons here? The hydrogens aren't shown. If I did it, it'd be like this. What's the hybridization on these oxygens? I mean, not like on the carbons. sp2. In fact, benzene's a flat ring because all these sp2 trigonal planar carbons are along the plane, right? And so when we do these, you know, like here, sp2 sigma bond, if we have an sp2 sigma bond, we're also going to have a p pi bond. The pi bonds are going to be, actually this is hard to see, right? to. So we got these sp2 orbitals, and then we have the p orbital kind of sticking out here, forming a pi bond. So this would be a p, I don't know, something like that. Do you guys remember that from 1A a little bit? All right, so the sp2 orbitals are in the plane. Where are the p orbitals in this ring? The p orbitals are perpendicular to the plane. So here's a lobe, here's a lobe. The p orbitals, and this is what gives this its aromatic properties. Do you see all the p orbitals are lined up? And so what we can do is we can delocalize the, right now this double bond is localized between this carbon, but what we can do is we can delocalize the pi bonding electrons over the entire ring. In other words, spread out the pi electron density evenly. Does that make sense? Yeah. What's the hybridization on this one here? sp3. Is sp3 flat in the plane? No. But we got to think, what is the reason for hybridizing atoms? There are two main things we think about when we hybridize atoms. In other words, why bother hybridizing?
More stable.
It's more stable because complete the shell, the valence shell. We don't have to hybridize to complete the valence shell. Two reasons for hybridizing. One, to maximize the bond thing. You know, carbon normally has only 2 unpaired electrons, therefore it could only form 2 bonds. But if we hybridize, promote, then we can form 4 bonds. And so maximize bonding, and 2, minimize repulsion to lower the energy. And so this one, if we did this, if we rehybridize this one to sp2, then one lone pair could stick in a p orbital like this, and the other one lone pair can stick in an sp2 here and an sp2 here. Then in this case, then if I have a lone pair in a p orbital here, and the p orbitals are lined up, then the electron density in the p orbital can be smeared out over the entire structure. Does that make sense there? It's going to cost energy to hybridize the sp2. It should work. The other way of visualizing this is like this. Yeah, okay, we can spread out the electron density because all the p orbitals are overlapping. Does this drawing make sense?
Yeah.
Okay. There's that redrawing. The other way we can think of this is happening is by rearranging the electron distribution. Like this. So this, we've got a negative charge here. So if we take this lone pair and drop it into the bond here, that's going to cause trouble for this. And so what we have to do is, we can't have 5 bonds to this carbon. And so one of these has to be kicked out, go on to this carbon here. So what that does is it generates this form here. All right, what did we convert the oxygen to? sp3 to sp2. So now this oxygen is sp2. This carbon is now sp3. And so it's no longer flat because this one's going to pop out or pop into the plane, but what we've done is we distributed this negative charge to this carbon. Now this carbon is going to have a negative formal charge. Well, what can we do with that? Well, one thing we can do with that is we can pop these in here and then pop this out here. And so we end up with this structure. And now the negative charge is here, right? Then we can repeat that. We can move these ones, these lone pair, into the bond here, make a pi bond, and break these ones here. Come out like this. If we do that, then we're going to get this structure here. And finally, if we place these into the bond here and then pop these ones out, we're back to where we started. And so do you see how the negative charge can be delocalized into the ring, making the conjugate base of phenol much more stable than you would expect for a typical alcohol? How about this? Which one would be more stable? In other words, which one should be a better acid? Why would the bottom one be a better acid? Because if you knock off the proton, then we got an oxygen with a negative charge. And then if we distribute the negative charge within the ring, having a chlorine here wouldn't help as much as having a chlorine here, because if we have a chlorine here, then when the negative charge comes here, it can be pulled towards chlorine via the inductive effect, and therefore it helps. And so having a chlorine here is helpful, or having a chlorine here is also helpful. Why is having a chlorine here helpful? Because the negative charge can end up here. Also, having a chlorine here is helpful. Why? Because negative charge can end up there. But having a chlorine here isn't going to be as helpful because the negative charge, do you see that? Doesn't end up on that carbon directly. And so organic chemists give these positions names: ortho, meta, para. And so ortho's good, meta's not as good, para's good. And so this is a combination of resonance, delocalization, and inductive effect, which helps to alter the acidity. So the most acidic of these three should be this one, this parachlorophenol right here. All right, so we have our data, and we're just trying to figure out. Most of the acids, they look like they are behaving nicely, and they look like they're lining up. But maybe that one outlier acid, it would be nice to know, why is that acid not behaving like the others? It's like HF. HI, HBr, HCl, and then all of a sudden HF is some kind of outlier. It's so much smaller than the others. You could just say, the trend goes this way, but it would be nice to say something about why HF doesn't behave like the others. And so the same thing, if you see an outlier acid in this, and there could be more, a lot more, we just didn't measure that many acids, right? or analyze that many acids. So you're going to take a look at the acids and then see if you can understand the ranking based on a structural analysis like this. All right. Are there any questions about the Spartan acids lab?
So we are drawing all of them, right?
The Lewis structures? Yeah, you have to draw all of them. All right, then we had a lab, the hydrolysis lab. Do you remember the hydrolysis lab? It's where you made the buffer solution.
Crystal violet.
Not the crystal violet. It's where you measured the pH of a whole bunch of different solutions, maybe 2 or 3 solutions. There are a lot of choices. And then you made a buffer solution and you added drop by drop strong acid or strong base to it to see how the pH changes. Do you guys do that?
Yeah.
Then you tried to overwhelm, that is add too much acid or base to overwhelm the buffer. All right, that the hydrolysis lab. Let's see. You don't have a report to turn in for that. Yeah, it's just going to be what you wrote in your notebook, observation. Okay, let me think.
What about the titration?
The titration lab, you have to write a formal
Report?
report for that one. You have to think about, when you're doing the titration report and your pKa's are off, you got to think about it. So I get this question asked quite often. And so during the hydrolysis lab, I try to give you a sense of how the pHs work, pH meters work. So I asked each group what pH they got for a solution. Do you recall what solution it was? Usually I try to do sodium hydrogen sulfate and then go around group by group and see what pH did you get for sodium hydrogen sulfate. Because everybody should get the exact same pH. It came out of the same bottle. And so I'll take a quick survey and see. And then the point was this. Everybody's pHs came out the same? No, the point was that there was a pretty wide spread of pHs. What implication does that have? That's actually not good, right? Because everybody's pH should be the same. But when I was going around surveying people, we seemed to have some variation in that. And so you have to think about that when you're thinking about pKa's, because where do your pKa's come from? The pHs, right? The pH meter and the pHs. Well, how accurate is that? Should be accurate. But as you saw, there was some variation. And so when you're analyzing your numbers, you have to weigh that you have to weigh that factor that there's a lot more variability in pHs. Whereas even if your pH meter is wrong, will the equivalence point show up at a different spot? No. I mean, let's say your pHs are reading 2 pH units too high. Well, it doesn't matter, just the y-axis changed a little bit. But where it goes up should be exactly the same in terms of milliliters. Okay. And so, since the titration report is kind of hard to analyze, have that as a formal report, so you can explain to me, how you're analyzing the data. That way, if you get the acid wrong, at least you get some credit for the analysis. And so, formal report for that. The rough draft is supposed to be due on Thursday, right? The second rough draft.
Oh, okay.
This Thursday, right? All right. What else? We have one more lab, the kinetics lab. The kinetics lab, I also like that to be a formal lab write-up because, some people get weird rate laws. So, for example, I've seen rate laws like this: K, CV plus K. I don't want K. I want the number with units. And then we need a number here for the order of CV plus. We need a number here for the order of hydroxide. And so let's say somebody got an order here, they got the hydroxide concentration of 1.5. And then some people will round that to 2, other people will round that to 1 because they like first order or second order. They don't like 1.5 order, right? Is that justifiable?
No.
Yeah, and then it might not be justifiable there. You've got to think about that. And so normally on the kinetics lab, I'd like to see, a formal report so you can explain everything you're doing to me. But we aren't going to do a formal report for this. So at the bare minimum, what you're going to do is turn in the spreadsheet and the graphs that we did in the computer lab.
Okay.
You should also, do some extra. That's a bare minimum. Bare minimum doesn't necessarily mean an A grade, It just means acceptable. You should also talk about your numbers. Does that make sense to have somebody got 1.7? Does that make sense? 1.7 order. What is 1.7 order? Maybe we should round it to 2. Yeah, not 1, not 2. Is it possible to have fractional orders or
Yes.
0.7 order, that? And so a little comment about that because a lot of people say it's impossible. Okay. All right, that's all we have time for today, but tomorrow we're going to continue. Yeah, this morning I got asked a lot of questions about the lab, so that's why I'm keeping classes in sync. Tomorrow we're going to finish the electrochem.
So, around like that, yeah, having a lot of